Hello students, in this video we are going to learn about vector spaces. To begin with, let us see the definition of a vector space. For defining a vector space, we need to begin with the set V, which we are going to call it as a vector space, and it is going to be a collection of objects, probably called as vectors. Now, for example, you can have your Rn, where n could be greater than or equal to 1. We could have the space of m by n matrices. We could have the space of functions, continuous functions on a closed interval, and we could have polynomials. Furthermore, what we need to do is we need to define an operation to add the two vectors, and that of course we are going to call it as addition, and we'll be denoting it by plus. In case for Rn, let us take a vector x bar, which would be of x1, x2 up to xn, and let's take another vector y bar, which would be y1, y2 up to yn. Then we know to add x bar and y bar, and it is nothing but the sum of corresponding elements in the n tuple. So this operation is called as addition. In addition, we need to define another operation, scalar multiplication. We'll denote the scalar multiplication by dot. So suppose say we have a vector x bar again in Rn, and suppose we take a scalar alpha in F. Now F is a field. F could be equal to either R or complex. Then we define scalar multiple as alpha times x, and that is going to be alpha x1, alpha x2 up to alpha xn. We need a set of vectors V, we need an operation addition, and we need a scalar multiplication. After this, what we are going to do is we are going to check a number of conditions. If those conditions are satisfied, then we say that V is going to be a vector space with these two operations. The first one is closure of addition. So by closure of addition, it means that if I take two vectors u and v in the vector space V, then u plus v should also be a member of V. That means the answer cannot go out of V. The second condition is commutativity of plus. By commutativity of plus, we say that u plus v must be same as v plus u. The third condition is associativity. And by that we mean if we have more than two vectors, then the addition can be done taking any two vectors into consideration. Then we must have the additive identity denoted by 0 bar. And the property which 0 bar must satisfy is that u plus 0 bar should always be u. And also we are looking out for inverses. That is, for any vector u in V, I should have a negative u in V, so that whenever we add u and negative u, we are going to get the additive identity. Furthermore, we look out for certain conditions based on scalar multiplication. So closure of scalar multiplication is the first condition. That means if I have a scalar alpha in the field F and a vector u in V, then alpha times u should also be contained in V. The second condition is the existence of identity with respect to scalar multiplication. We know that there is a 1 which when multiplied by u is going to keep it u. We have the compatibility conditions. The compatibility condition states that alpha beta times u is going to be same as alpha times beta u. And lastly, we have distributivity between vector addition and scalar multiplication, and that can be stated as alpha plus beta times u is equal to alpha u plus beta u, while alpha times of u plus v is going to be alpha u plus alpha v. If any set V satisfies these 9 conditions, with respect to addition as well as scalar multiplication, then we say that V is going to form a vector space. And the choice of scalar, if F is taken to be real, then we say that V is a real vector space. If F is going to be taken as complex, then we say that the vector space is a complex vector space. Thank you everyone.